The night sky erupted in brilliance on October 28, 2025, as astronomers worldwide witnessed something that would fundamentally challenge our understanding of stellar behavior and cosmic mechanics. At 23:47 UTC, the interstellar visitor 3I Atlas suddenly flared to 10 times its previous brightness, transforming from a distant fuzzy dot into a spectacular celestial firework visible to the naked eye. Dr. Elena Rodriguez was conducting routine observations at the Palomar Observatory when her computer screens lit up with alerts. "I thought it was an instrument malfunction at first," she later recalled. The brightness readings were off the charts, but when I looked through the eyepiece, I saw something that shouldn't exist. 3 Atlas was breaking apart in real time. The destruction was immediate and catastrophic. Through her telescope, Dr. Rodriguez watched as the ancient interstellar visitor that had travelled for millions of years between star systems was reduced to an expanding cloud of glowing debris in a matter of minutes. The nucleus that had survived the hostile environment of interstellar space was completely shattered, sending fragments racing in all directions at velocities that would carry them throughout the solar system. Within hours, observatories across 6 continents confirmed the unprecedented event. The Atacama Large Millimeter Array in Chile detected massive radio emissions from the collision site. The Very Large Telescope in Paranal captured spectacular images of the expanding debris field. The Hubble Space Telescope was immediately redirected to provide high-resolution imagery of the destruction. Dr. James Chen at the Harvard-Smithsonian Center for Astrophysics found himself coordinating an international response as telescopes around the world focused on the collision site. Emergency protocols that had been developed for asteroid impact scenarios were activated, even though this event was occurring millions of kilometers from Earth. "We're witnessing the violent destruction of an object that has traveled between star systems for potentially millions of years," Dr. Chen explained during an emergency press conference at 3 a.m. Eastern Time. Whatever hit 3I Atlas was massive, fast-moving, and completely unexpected. We have no record of any object on a collision course with the comet. The initial spectroscopic analysis of the collision site revealed a complex mixture of exotic ices, rocky debris, and high-temperature plasma that suggested an impact of extraordinary violence. The collision had released energy equivalent to thousands of nuclear weapons, completely vaporizing portions of both the projectile and the target. The plasma cloud at the impact site glowed with temperatures exceeding 100,000 Kelvin, hot enough to ionize virtually any known material. The extreme temperatures suggested that the collision had involved velocities far exceeding anything previously observed in natural solar system processes. Dr. Sarah Martinez, director of NASA's Planetary Defense Coordination Office, found herself managing a crisis that had no precedent in human experience. The Planetary Defense Network had been designed to track and potentially deflect objects threatening Earth, but had never dealt with the aftermath of a major collision involving interstellar material. "We're dealing with the aftermath of an impact involving interstellar material," she explained to a packed briefing room at NASA headquarters. "The debris carries velocities and compositions unlike anything in our solar system, which makes predicting their trajectories extremely challenging." The fragments of 3I Atlas displayed orbital characteristics that defied conventional tracking algorithms. Computer models designed to predict asteroid and comet trajectories were based on objects that had formed within our solar system and followed predictable gravitational mechanics. The collision debris carried energy and momentum from interstellar space that created trajectories unlike anything in the databases. Some fragments maintained hyperbolic trajectories that would carry them out of the solar system entirely, continuing the interstellar journey that 3I Atlas had begun millions of years ago. Other pieces appeared to have been slowed enough by the collision to become temporarily bound by solar gravity, creating new artificial satellites with highly elliptical orbits. The largest fragments were estimated to be several hundred meters across, large enough to cause significant damage if they impacted a planet or moon. Smaller debris range from basketball-sized chunks down to microscopic particles, all carrying the exotic chemistry that had made 3I Atlas so scientifically valuable. Within 24 hours of the collision, tracking stations around the world had catalogued over 15,000 individual fragments large enough to detect with radar. The actual number of pieces was estimated to be in the millions when particles too small for current detection methods were included. The European Space Agency's Space Debris Office expanded its mission beyond tracking artificial satellites to monitor the 3I Atlas debris field. New tracking algorithms were developed specifically for objects with interstellar velocities and compositions, requiring fundamental modifications to existing orbital mechanics software. As the initial shock of the collision subsided, attention turned to identifying the mysterious projectile that had destroyed the interstellar visitor. The complete absence of any detected incoming object in the days leading up to the impact suggested that whatever struck 3I Atlas had either been too small to detect with current instruments or had approached from an unexpected direction. Dr. Michael Thompson at the Jet Propulsion Laboratory led an international team tasked with reconstructing the projectile's characteristics using data from the collision itself. By analysing the velocity vectors of the fragments, the energy release from the impact, and the spectroscopic signatures of the plasma cloud, his team began piecing together clues about the object that had caused such spectacular destruction. The impact dynamics suggest we're dealing with something unprecedented, Dr. Thompson reported to an emergency session of the International Astronomical Union. The projectile appears to have been travelling at extremely high velocity. Our preliminary estimates suggest speeds exceeding 200 kilometers per second. That's far faster than any known natural object in our solar system. The extreme velocity implied several disturbing possibilities. The projectile might have been another interstellar visitor that had intercepted 3I Atlas's trajectory through cosmic coincidence. Alternatively, it could have been accelerated by some unknown mechanism within our solar system to speeds that exceeded normal orbital mechanics. The absence of any detected incoming object raised questions about the limitations of current space surveillance systems. If projectiles capable of destroying major cosmic objects could approach undetected, what did this mean for planetary defense capabilities? Were there natural phenomena in space that could threaten Earth without warning? Dr. Lisa Park at the Solar Dynamics Observatory began analysing solar activity data from the weeks preceding the collision, searching for any unusual events that might explain the apparent connection between the impact and solar phenomena. Her investigation would lead to discoveries that challenged fundamental assumptions about stellar behaviour. The spectroscopic analysis of the plasma cloud at the collision site revealed chemical signatures that didn't match typical interstellar material or known solar system compositions. Instead, the plasma showed characteristics consistent with highly ionized solar material, the kind of superheated gas normally found only in the sun's corona or in the most energetic coronal mass ejections. The plasma signatures we're seeing aren't consistent with a typical asteroid or comet impact, Dr. Park announced during a hastily convened video conference with solar physicists worldwide. They match the spectral characteristics of solar ejecta, material that originated from our sun's corona. The implication was staggering and initially met with skepticism from the scientific community. If the plasma signatures were correct, the projectile that destroyed 3I Atlas had somehow originated from solar activity rather than from another interstellar object or rogue asteroid. But how could the sun launch material with enough coherence and velocity to travel astronomical distances and strike a specific target? Solar physicists had studied coronal mass ejections for decades and understood them to be diffuse clouds of ionized gas that dispersed as they traveled through space, Typical CMEs lost coherence within hours or days of ejection, spreading their material across millions of cubic kilometers. The idea that solar ejecta could maintain focus structure across interplanetary distances contradicted established understanding of plasma physics. Dr. Roberto Silva at the National Solar Observatory was tasked with reviewing 3 weeks of solar observation data leading up to the 3I Atlas collision. The search required analyzing terabytes of information from multiple spacecraft and ground-based instruments monitoring solar activity. What Dr. Silva discovered challenged every assumption about how the Sun behaved. On October 7th, 3 weeks before the collision, the Solar Dynamics Observatory had recorded a series of unusual coronal mass ejections that displayed characteristics unlike anything in the historical record. We're looking at solar ejecta that behaved more like projectiles than typical coronal mass ejections, Dr. Silva explained to his increasingly stunned colleagues. The magnetic field configurations and plasma dynamics suggest these events were somehow focused and directed rather than following the normal expansion patterns we expect from solar activity. The unusual CMEs had originated from a complex active region on the Sun's surface where magnetic field lines had become twisted into configurations that solar physicists had never observed. Instead of the typical chaotic tangle of magnetic fields that characterized most active regions, this area showed highly organized structures that created natural focusing mechanisms for ejected plasma. High-resolution magnetograms from the Solar Dynamics Observatory revealed magnetic field patterns that resembled the configuration of a natural particle accelerator. Plasma ejected from this region was guided and focused by magnetic forces that prevented the normal dispersal observed in typical coronal mass ejections. Dr. Patricia Williams at the Princeton Plasma Physics Laboratory was brought in to analyze the magnetic field configurations and their potential for creating focused plasma streams. Her expertise in controlled fusion and magnetic confinement provided crucial insights into how the Sun might have achieved the impossible. We're seeing magnetic field configurations that create natural plasma railguns in the solar corona, she reported to the International Research Consortium. Under very specific conditions, these configurations can accelerate ionized material to incredible velocities while maintaining coherent structure across astronomical distances. The plasma railgun analogy provided a framework for understanding how the Sun might have launched projectiles capable of intercepting 3I Atlas. But it raised even more profound questions about whether such events were random occurrences or represented some form of directed solar behavior. Detailed analysis of the magnetic field evolution in the active region revealed that the focusing configuration had developed over several days through a process that appeared to be influenced by external electromagnetic stimuli. The timing of the magnetic field changes corresponded closely to increases in electromagnetic activity from 3I Atlas as it approached the inner solar system. Dr. Jennifer Walsh at the University of Colorado began investigating whether the solar focusing events might be connected to the electromagnetic phenomena that 3I Atlas had been generating during its approach. Previous research had documented correlations between the comet's radio emissions and increased solar activity, but no one had considered the possibility of directed solar responses. We need to consider the possibility that 3I Atlas was somehow triggering the very solar events that ultimately destroyed it, Dr. Walsh explained to the International Research Committee. The electromagnetic coupling between the comet and our Sun might have created a feedback loop that culminated in the focused plasma ejection. The feedback loop hypothesis suggested that 3I Atlas had been inadvertently provoking solar responses that built in intensity over time. The comet's exotic electromagnetic emissions, generated by its unusual chemistry and the interaction of its coma with solar radiation, might have destabilized solar magnetic fields in ways that eventually led to the focused ejection events. Computer simulations of the proposed electromagnetic coupling were conducted at supercomputing centers around the world. The models attempted to reproduce the interaction between 3I Atlas's electromagnetic signature and the complex magnetic field structures in the solar corona. The simulations revealed that the comet's emissions could indeed create resonance effects in solar plasma oscillations. When electromagnetic waves from 3I Atlas interacted with plasma in the solar corona, they could amplify existing magnetic instabilities and trigger cascade effects that led to much larger disturbances. Dr. Robert Chen at the Max Planck Institute for Solar System Research led the effort to model the complete sequence of events from initial electromagnetic coupling to final plasma ejection. The work required incorporating effects from multiple physics disciplines, including plasma dynamics, electromagnetic field theory, and nonlinear resonance phenomena. The comet essentially created a tuning fork effect in the solar corona, Dr. Chen explained. Its electromagnetic emissions resonated with natural oscillation frequencies in solar plasma, amplifying magnetic disturbances until they reached the threshold for focused ejection events. The resonance effects created a scenario where 3I Atlas had induced its own destruction through electromagnetic interference with solar dynamics. The interstellar visitor's alien chemistry and electromagnetic properties had triggered solar responses that culminated in directed plasma ejection, powerful enough to shatter the comet's nucleus. The timing analysis revealed an inexorable progression from initial electromagnetic coupling to final destruction. As 3I Atlas approached closer to the Sun, its electromagnetic emissions strengthened, creating more intense resonance effects in solar plasma. The feedback loop amplified over time until the magnetic stresses in the corona exceeded the threshold for focused ejection. The focused solar ejector traveled at velocities that allowed them to intercept 3I Atlas at its predicted location along its orbital trajectory. The precision of the targeting was achieved through electromagnetic homing effects that guided the plasma projectiles toward the source of the resonant emissions. As the investigation into the collision mechanism continued, the expanding debris field created new challenges and opportunities for scientific study. Fragments of 3I Atlas now carried authentic interstellar material throughout the inner solar system, providing unprecedented opportunities for direct analysis of matter from another star system. The distribution of debris followed complex patterns determined by the impact dynamics and the gravitational influences of planets and the Sun. Larger fragments maintained trajectories similar to the original comet, while smaller pieces were more easily deflected by planetary gravity and solar radiation pressure. Space agencies around the world began planning rapid response missions to intercept and study the larger fragments before they could escape the solar system or become impossible to reach. The window of opportunity was narrow, as most fragments would either leave the solar system entirely or become too distant for practical spacecraft missions within a few years. Dr. Amanda Foster at the European Space Agency led the planning for an ambitious sample return mission to one of the largest intact fragments. The mission, designated Phoenix Atlas, would need to be designed, built, and launched within 18 months to have any chance of reaching its target. We have an unprecedented opportunity to collect samples of authentic interstellar material, she explained to a joint meeting of space agency directors. The fragments contain matter that formed around another star billions of years ago. This may be our only chance to study such material in detail. The Phoenix Atlas mission required revolutionary advances in rapid spacecraft development and autonomous navigation. Traditional mission planning timelines of 5 to 10 years were compressed into months as engineers worked around the clock to design spacecraft capable of reaching fragments traveling at interstellar velocities. Multiple space agencies coordinated their efforts to maximize the chances of successful sample collection. NASA, ESA, JAXA, Roscosmos, and other organizations pooled resources and expertise to launch a constellation of small, fast spacecraft designed to intercept different fragments and return samples to Earth. The engineering challenges were unprecedented. The spacecraft needed to match velocities with fragments traveling at speeds of 50 to 200 kilometers per second, collect samples without destroying themselves, and return to Earth with their precious cargo intact. No existing spacecraft design could handle such extreme requirements. Breakthrough propulsion technologies were developed specifically for the fragment intercept missions. Ion drives with unprecedented power-to-weight ratios were designed to provide the velocity changes needed to match fragment trajectories. New heat shield technologies were created to protect spacecraft during high-speed intercepts. The first fragment intercept mission launched just 14 months after the collision, setting records for rapid mission development and deployment. The Phoenix 1 spacecraft targeted a 500-meter fragment that had been slowed enough by the collision to remain within range of Earth-based missions. During its approach to the target fragment, Phoenix 1 transmitted unprecedented close-up images of interstellar material. The fragment showed evidence of complex internal structure with layers of different compositions, suggesting that 3I Atlas had undergone multiple formation episodes during its billion-year journey between stars. The sample collection process required delicate maneuvering to extract material without damaging the spacecraft or contaminating the samples with Earth-based material. Robotic arms guided by artificial intelligence systems performed the collection autonomously, as the distance to Earth made real-time control impossible. Phoenix 1's successful sample return marked the first time humanity had obtained direct physical samples of interstellar material. The fragments arrived on Earth in specially designed containment systems that prevented contamination and preserved the exotic chemistry that made them scientifically invaluable. Dr. Maria Santos at the Meteorite Research Institute led the analysis of the first recovered fragments. The work required developing new analytical techniques capable of handling material with compositions unlike anything found in the solar system. We're looking at matter that formed around another star when our solar system didn't even exist, she reported during a press conference that was broadcast worldwide. The isotopic ratios and mineral compositions tell a story of stellar evolution and planetary formation under conditions completely different from our local cosmic neighborhood. The fragment analysis confirmed that 3I Atlas had indeed originated from a stellar system with dramatically different characteristics than our Sun. The material showed evidence of formation around a low-mass M-dwarf star, with subsequent processing by cosmic ray bombardment during millions of years of interstellar travel. Some fragments contained complex organic molecules that had survived both the interstellar journey and the violent collision that destroyed their parent object. These molecules provided the first direct evidence of organic chemistry from another stellar system, offering tantalizing clues about the potential for life in interstellar environments. The organic chemistry found in the fragments included amino acid precursors, nucleotide bases, and complex hydrocarbon structures that were similar to, but not identical to, the building blocks of terrestrial life. The discovery suggested that the chemical foundations for biology might be common throughout the galaxy, but with variations that reflected different stellar environments. Dr. Jennifer Kim at the Astrobiology Institute led research into the biological implications of the organic molecules found in 3I Atlas fragments. While no definitive evidence of past or present life was discovered, the presence of complex organics suggested that the prerequisites for life existed in other stellar systems. The discovery of intact organic molecules in the fragments raised questions about whether interstellar objects like 3I Atlas might serve as vehicles for distributing biological material throughout the galaxy. If complex organics could survive million-year journeys between stars, the potential for life to spread across vast cosmic distances was much higher than previously estimated. Astrobiology research programs expanded dramatically following the fragment analysis results. New funding supported investigations into how life might survive in interstellar environments and how biological material might be distributed between stellar systems through natural cosmic processes. The implications for the search for extraterrestrial life were profound. If interstellar visitors routinely carried complex organic chemistry between star systems, the galaxy might be more biologically connected than anyone had imagined. Life on Earth might have interstellar origins, and terrestrial life might contribute to the biological diversity of other worlds through natural exchange processes. As months passed and additional fragment recovery missions returned with samples, a comprehensive picture of 3I Atlas's composition and history began to emerge. The destroyed comet had been a repository of information about stellar evolution, planetary formation, and galactic chemical evolution spanning billions of years. Different fragments provided snapshots of different episodes in 3I Atlas's long journey. Some samples showed evidence of formation in the original protoplanetary disk around its parent star. Others revealed chemical processing that had occurred during its interstellar transit, including bombardment by cosmic rays and interaction with interstellar dust clouds. The chemical timeline preserved in the fragments provided unprecedented insights into how matter evolved during interstellar journeys. Material that began as simple ices and rocky particles around another star had been transformed into complex chemical systems through cosmic processes that operated over millions of years. Dr. Thomas Anderson at the Institute for Stellar Chemistry led efforts to reconstruct the complete chemical evolution of 3I Atlas from its formation to its destruction. The work required developing new analytical techniques and theoretical models for understanding how matter changed during interstellar travel. We're essentially reading the chemical biography of an object that has experienced cosmic processes we can barely imagine, Dr. Anderson explained. Every isotopic ratio and molecular structure tells us something about stellar nucleosynthesis, cosmic ray interactions, and chemical evolution in interstellar space. The chemical biography revealed that 3I Atlas had encountered multiple different environments during its journey between stars. Evidence suggested that it had passed through several molecular clouds, each with different chemical compositions and physical conditions that had influenced its evolution. Some fragments showed evidence of heating events that had occurred during the interstellar journey, possibly from encounters with stellar radiation or shockwaves from supernova explosions. These heating episodes had altered the mineral structures and organic chemistry in ways that provided information about the galactic environment that 3I Atlas had travelled through. The stellar chemistry research revealed that the parent star of 3I Atlas had been significantly different from our Sun. Isotopic ratios indicated that it had been a lower mass star with unusual abundances of certain heavy elements, suggesting formation during an earlier epoch of galactic evolution when stellar chemistry was different from today. Nuclear physics analysis of the fragments provided information about the nuclear processes that had occurred in the core of 3I Atlas's parent star. The isotopic signatures revealed details about stellar evolution, nucleosynthesis, and the cosmic recycling of heavy elements that had created the raw materials for planet formation. The destruction of 3I Atlas had created the most comprehensive dataset about interstellar material ever obtained by human science. Every fragment provided new information about cosmic processes that operated on scales of time and distance that dwarfed human experience. Meanwhile, research into the solar focusing mechanism that had destroyed the comet continued to yield disturbing insights about stellar behavior and cosmic dynamics. The discovery that our Sun could launch directed plasma projectiles in response to electromagnetic stimuli raised fundamental questions about stellar physics and galactic evolution. Dr. Catherine Lee at the Stellar Dynamics Laboratory began investigating whether other stars showed evidence of similar focused ejection capabilities. Analysis of stellar observation data from space-based telescopes revealed that several nearby stars had displayed unusual coronal activity that might represent focused plasma ejection phenomena. We might be seeing evidence that stars throughout our local galactic neighborhood are capable of launching directed plasma projectiles, Dr. Lee reported to the International Astronomical Union. If this is a common stellar phenomenon, it could explain why interstellar visitors are much rarer than theoretical predictions suggest they should be. The stellar defense mechanism hypothesis proposed that star systems might naturally protect themselves from interstellar intrusions through focused plasma ejection. The electromagnetic signatures of approaching interstellar objects could trigger stellar responses that eliminated potential threats before they could significantly influence planetary system dynamics. Computer simulations of galactic dynamics incorporating stellar defense mechanisms revealed that such phenomena could significantly alter the distribution and survival of interstellar objects. Stars that actively eliminated foreign objects would create relatively empty zones around themselves, reducing the frequency of interstellar encounters. The implications for interstellar travel and communication were sobering. If stars actively defended themselves against foreign objects, any attempt by human civilization to send spacecraft to other star systems might face similar hostile responses. The cosmos might be far more actively defensive than anyone had previously imagined. Alternative interpretations of the solar focusing events emerged as researchers considered different explanations for the unprecedented phenomena. Some scientists proposed that the focused ejections might represent natural stellar behavior that occurred regularly but had simply never been observed with sufficient precision to document properly. Dr. Helen Morrison at the Astrophysics Research Institute suggested that stars might routinely eject focused plasma streams as part of normal magnetic field evolution. We might be witnessing natural stellar processes that occur regularly, but are usually too subtle or poorly aimed to create observable effects, she explained. The natural phenomena hypothesis was supported by theoretical models showing that magnetic field evolution in stellar coronas could indeed create focusing effects under specific conditions. The focusing might represent a natural consequence of stellar magnetic dynamics rather than a defensive response to external threats. However, the precision of the targeting that destroyed 3I Atlas seemed to exceed what could be explained by random magnetic evolution. The solar ejector had been aimed with remarkable accuracy toward the comet's predicted location, suggesting either extraordinary coincidence or some form of guided targeting mechanism. Research into the targeting mechanism revealed that electromagnetic feedback between 3I Atlas and solar plasma might have created a homing effect that guided the plasma projectiles toward their target. The comet's electromagnetic emissions could have acted as a beacon that the focused solar ejector followed to impact. Dr. Paul Richards at the Electromagnetic Dynamics Laboratory developed detailed models showing how electromagnetic resonance between the comet and solar plasma could create attractive forces that would pull focused ejector toward the source of electromagnetic disturbance. The comet essentially painted a target on itself, Dr. Richards explained. Its electromagnetic emissions created a resonance pattern in solar plasma that acted like a guidance system for the focused ejection events. The plasma projectiles were naturally drawn to the source of the electromagnetic disturbance. The electromagnetic homing mechanism provided a plausible explanation for the apparent precision of the solar targeting without requiring deliberate stellar intelligence or artificial guidance systems. The physics of plasma electromagnetic interaction could account for the observed accuracy through natural attraction effects. The homing effect also explained why the timing of the ejection events had been so precisely coordinated with 3I Atlas's orbital position. The electromagnetic coupling created a real-time guidance system that allowed the plasma projectiles to track the moving target across astronomical distances. As the first anniversary of the collision approached, the scientific community had developed a comprehensive understanding of the physical mechanisms that led to 3I Atlas's destruction. The interstellar visitor's exotic electromagnetic properties had triggered solar responses that culminated in focused plasma ejection, powerful enough to shatter the comet's nucleus. The destruction had revealed that our solar system was far more dynamic and reactive than previously understood. The Sun was capable of launching directed projectiles in response to electromagnetic stimuli, creating a form of stellar defense mechanism that could eliminate interstellar intruders through natural physical processes. The implications extended far beyond the immediate scientific discovery to influence humanity's understanding of cosmic evolution, interstellar travel, and the potential for material exchange between stellar systems. The universe had revealed itself to be more actively structured and potentially hostile to interstellar migration than anyone had previously imagined. The technological developments inspired by studying the collision had already begun to influence human technology and space exploration capabilities. Understanding how the Sun could focus and direct plasma streams had opened new possibilities for controlled fusion power generation and advanced spacecraft propulsion systems. Plasma confinement research had made breakthrough advances by applying principles discovered in the study of solar focusing mechanisms. Fusion reactor designs incorporating stellar-inspired magnetic field configurations showed promise for achieving controlled nuclear fusion with unprecedented efficiency and stability. Advanced propulsion concepts based on focused plasma acceleration offered potential solutions for interplanetary and eventually interstellar travel. The same principles that allowed the Sun to launch projectiles across astronomical distances might be scaled down and controlled for spacecraft propulsion applications. Space exploration programs began incorporating the lessons learned from the 3I Atlas collision into planning for future interstellar missions. Any spacecraft sent to other star systems would need to account for the possibility of encountering directed stellar responses to their electromagnetic signatures. Electromagnetic shielding technologies were developed to protect spacecraft from focused plasma streams and other stellar defense mechanisms. The designs incorporated lessons learned from studying how material survived the 3I Atlas collision and the protective effects of different shielding configurations. Planetary defense strategies expanded beyond tracking incoming asteroids and comets to consider the potential for solar responses to create hazardous conditions within our own solar system. The focused ejection events that destroyed 3I Atlas demonstrated that our Sun could generate threats that extended far beyond typical space weather phenomena. International cooperation in space science reached unprecedented levels as nations recognized that stellar phenomena transcended terrestrial boundaries and affected all of humanity equally. The lessons learned from studying 3I Atlas's destruction required global coordination to implement effectively. The Global Space Weather Consortium was established to monitor stellar activity and provide early warning of potential focusing events that might threaten spacecraft or create hazardous space weather conditions. The organization coordinated observations from space-based and ground-based instruments worldwide, Educational curricula were expanded to include lessons about stellar dynamics, plasma physics, and the active nature of cosmic environments. Students learned that space was not empty and passive, but filled with dynamic processes that could affect human activities and technological systems. The cultural impact of witnessing stellar destruction of an interstellar visitor resonated through human society in ways that extended far beyond scientific circles. The event had demonstrated that even objects that survived million-year journeys between stars could be eliminated by stellar activity, highlighting the hostile and dynamic nature of cosmic environments. Religious communities grappled with theological implications of stellar systems that appeared to defend themselves against foreign intrusion. Some interpreted the destruction of 3i Atlas as evidence of divine protection for stellar systems, while others saw it as demonstration of the cosmos's inherent violence and unpredictability. Philosophical discussions emerged about cosmic purpose and design. If stars naturally eliminated interstellar visitors, the universe might be structured in ways that prevented rather than facilitated communication and interaction between civilizations. The cosmos might be actively hostile to the spread of life and intelligence between worlds. Environmental organizations used the 3i Atlas destruction to advocate for protecting Earth's biosphere from cosmic threats, while also recognizing that our solar system possessed natural defensive capabilities. The balance between cosmic protection and cosmic isolation became a new theme in environmental philosophy and policy. Economic implications of the collision continue to manifest as industries adapted to new understanding of space weather and stellar activity. Satellite operators implemented enhanced protection against focused plasma events, while space tourism companies reconsidered the safety of operations during periods of increased solar activity. The insurance industry struggled to assess risks associated with stellar phenomena that had no historical precedent. New actuarial models were developed to account for the possibility of directed solar events that could affect spacecraft, satellites, and even ground-based infrastructure through enhanced space weather effects. Agricultural monitoring programs expanded to include assessment of how stellar ejection events might affect Earth's magnetosphere and atmospheric chemistry. The focused plasma events that destroyed 3i Atlas demonstrated that solar activity could reach intensity levels that might significantly influence terrestrial environmental conditions. Research funding for space science increased dramatically as governments recognized the importance of understanding stellar dynamics and cosmic threats. The 3i Atlas collision had demonstrated that cosmic events could have immediate practical implications for human technology and safety. Commercial space companies accelerated development of radiation-hardened technologies and enhanced space weather monitoring systems. The demonstrated ability of solar activity to create focused plasma streams required new approaches to spacecraft design and mission planning. As the second anniversary of the collision approached, long-term monitoring programs continued to track the dispersal of 3i Atlas fragments throughout the solar system. Some pieces had already begun to leave the solar system entirely, continuing the interstellar journey that their parent object had begun millions of years ago. Other fragments had been captured into stable orbits around planets and remained accessible for future study. These captive pieces of interstellar material provided long-term laboratories for studying how exotic matter evolved under different environmental conditions. Mars received several fragment impacts that created new craters containing authentic interstellar material. Future Mars missions would have opportunities to study these impact sites and analyze interstellar chemistry in the Martian environment. Jupiter's powerful gravitational field captured numerous larger fragments into highly elliptical orbits, creating temporary moons composed entirely of interstellar material. These captured objects offered unprecedented opportunities for detailed study of matter from another star system. The Moon received hundreds of small fragment impacts that were documented by lunar monitoring systems. The impact sites provided natural laboratories for studying how interstellar material behaved when exposed to the lunar environment and solar radiation. Asteroid belt dynamics were subtly altered by the passage of high-velocity fragments through the region between Mars and Jupiter. Some fragments gravitationally perturbed existing asteroid orbits, creating new near-Earth object populations that required monitoring and assessment. The outer solar system received numerous fragments that would remain in distant orbits for millions of years. These objects created a permanent reservoir of interstellar material within our solar system's boundaries, ensuring that future generations would have access to authentic samples from another star system. The scientific legacy of the 3I Atlas collision extended far beyond the immediate discoveries about stellar defense mechanisms and interstellar chemistry. The event had demonstrated that individual cosmic encounters could have far-reaching consequences that affected entire planetary systems and influenced the course of scientific and technological development. Universities worldwide established new research programs focused on stellar dynamics, plasma physics, and interstellar material science. The collision had created entirely new fields of study that combined traditional astronomy with plasma physics, electromagnetic dynamics, and materials science. The interdisciplinary nature of the research had broken down traditional academic boundaries and created new forms of scientific collaboration. Physicists worked with astronomers, materials scientists collaborated with plasma physicists, and engineers developed new technologies based on cosmic phenomena. International scientific cooperation reached levels that had never been achieved in peacetime. The global response to the 3I Atlas collision had demonstrated that humanity could work together effectively when faced with cosmic-scale challenges that transcended national boundaries and political differences. The technological developments inspired by studying the collision had practical applications that benefited all of human civilization. Advances in plasma physics contributed to clean energy development, while improvements in electromagnetic shielding protected both spacecraft and terrestrial infrastructure from space weather effects. Medical applications emerged from research into how matter behaved under the extreme conditions created by focused plasma impacts. New cancer treatment techniques were developed based on understanding how high-energy particles affected biological materials at the cellular level. Materials science breakthroughs led to development of new substances with properties that had never been achieved through terrestrial manufacturing processes. The extreme pressures and temperatures created during the 3I Atlas collision had produced material phases that could be studied and potentially replicated for technological applications. Communication technologies benefited from understanding how electromagnetic signals propagated through plasma environments and how focused electromagnetic fields could be generated and controlled. These advances led to more efficient wireless communication systems and improved radio astronomy capabilities. Transportation systems incorporated lessons learned about high-velocity impacts and plasma dynamics. New safety systems for aircraft and spacecraft were developed based on understanding how objects behaved during extreme velocity encounters. Manufacturing processes were revolutionized by application of controlled plasma focusing techniques derived from studying solar ejection mechanisms. New industrial processes could create materials with properties that were previously impossible to achieve. As the third anniversary of the collision approached, the expanding sphere of 3I Atlas fragments had grown to encompass much of the inner solar system. The debris field served as a permanent reminder of the day when humanity learned that stars could actively defend themselves, and that the cosmos was far more dynamic and potentially hostile than anyone had previously imagined. The fragments continued to provide scientific data about interstellar processes and cosmic chemistry. Each piece carried information about stellar evolution, galactic dynamics, and the harsh environment of interstellar space that was impossible to obtain through any other means. Space missions continued to intercept and study fragments as they dispersed throughout the solar system. The extended duration of sample collection opportunities allowed for comprehensive analysis of different types of material and chemical compositions that had been present in the original comet. Ground-based telescopes maintained continuous monitoring of the larger fragments, tracking their evolution as they were affected by solar radiation, cosmic ray bombardment, and interactions with the solar wind. The observations provided real-time data about how interstellar material changed when exposed to solar system environments. The collision site itself continued to provide valuable scientific information. The plasma cloud that had been created by the impact gradually dispersed, but spectroscopic analysis continued to yield insights about the physical processes that had occurred during the destruction event. Radio telescopes detected long-term electromagnetic effects from the collision site, including plasma wave propagation and magnetic field disturbances that persisted for years after the initial impact. These phenomena provided information about how cosmic collisions affected the electromagnetic environment of space. The impact had created a permanent alteration to the local space environment that would be detectable for decades. Future spacecraft missions to the collision region would find electromagnetic anomalies and residual plasma effects that served as a cosmic archaeology site, preserving evidence of the dramatic event. As research into the collision continued, new questions emerged about the frequency and distribution of such events throughout the galaxy. If stellar defense mechanisms were common, the space between stars might be regularly swept clean of interstellar debris by focused plasma ejections from billions of active stars. Galactic evolution models began incorporating the effects of stellar defense mechanisms on the distribution of interstellar material and the survival rates of objects traveling between star systems. The cosmos might be far more actively structured and organized than random gravitational processes alone could explain. The implications for the search for extraterrestrial intelligence and interstellar communication were profound. If stars actively defended themselves against foreign objects, any civilization attempting to expand beyond its home system might face systematic destruction by stellar activity throughout the galaxy. Alternative scenarios for galactic evolution emerged that took into account the active role of stellar systems in shaping the distribution of interstellar material. The traditional model of passive gravitational interactions was replaced by dynamic systems, where stars actively influenced their cosmic neighborhoods through focused energy projection. Dr. Michael Harrison at the Institute for Advanced Cosmology began developing new theoretical frameworks for understanding galactic structure in light of stellar defense mechanisms. His work suggested that the observed distribution of star systems and interstellar material might reflect billions of years of active stellar intervention rather than purely random gravitational processes. We're looking at a galaxy where stars actively shape their local environments through energy projection, Dr. Harrison explained to the International Cosmological Society. The empty regions between star systems might not be naturally empty, but rather actively maintained by stellar activity that eliminates interstellar debris and foreign objects. The active galaxy hypothesis provided explanations for several long-standing astronomical puzzles. The relative scarcity of interstellar objects, compared to theoretical predictions, could be explained by systematic elimination through stellar defense mechanisms. The observed clustering patterns of star systems might reflect cooperative stellar behavior rather than purely gravitational effects. Computer simulations of galactic evolution incorporating active stellar intervention produced results that more closely matched observed galactic structure than traditional gravitational models. Stars that could eliminate interstellar debris would create more stable planetary systems and reduce the frequency of catastrophic impacts that might disrupt biological evolution. The stability implications were particularly significant for understanding the development of life in the galaxy. If stellar defense mechanisms provided protection against interstellar bombardment, planetary systems might remain stable for much longer periods, allowing more time for complex life to evolve and develop technological civilizations. However, the same mechanisms that protected planetary systems from interstellar debris might also prevent the spread of life and technology between star systems. Any attempt by biological or artificial intelligence to travel between stars might trigger defensive responses that eliminated the travelers before they could establish themselves in new systems. The paradox of stellar defense created a new framework for understanding the apparent absence of extraterrestrial visitors to Earth. The Fermi paradox, which questioned why no alien civilizations had been detected despite the vast number of stars and potentially habitable planets, might be explained by natural barriers to interstellar travel created by stellar activity. Dr. Sarah Thompson at the SETI Institute began reassessing the search strategies for extraterrestrial intelligence in light of the stellar defense discoveries. If civilizations were naturally confined to their home star systems by stellar activity, the search for alien signals might need to focus on detecting communications within individual stellar systems rather than between them. We might need to completely rethink our approach to searching for extraterrestrial intelligence, Dr. Thompson announced at the annual SETI conference. If stellar defense mechanisms prevent interstellar travel and communication, alien civilizations might be effectively quarantined within their home systems, making detection much more challenging. The quarantine hypothesis suggested that intelligent civilizations throughout the galaxy might be aware of each other's existence, but unable to establish direct contact due to natural stellar barriers. Each star system might contain isolated pockets of intelligence that developed independently but remained forever separated by cosmic-scale defense mechanisms. Alternative communication strategies were proposed that might circumvent stellar defense systems. Quantum entanglement communications, gravitational wave messaging, and neutrino transmissions might pass through stellar defense barriers without triggering protective responses. These exotic communication methods might represent the only viable means of interstellar contact between quarantined civilizations. Research programs were established to investigate whether Earth's radio communications might have triggered solar defensive responses in the past. The correlation between increasing human radio emissions and solar activity patterns was analysed to determine whether our own technology might be provoking stellar reactions. Preliminary analysis suggested that Earth's electromagnetic emissions were still too weak to trigger significant solar responses, but the potential for future technological developments to cross critical thresholds raised concerns about the long-term consequences of expanding human technology. Space agencies began incorporating stellar defense considerations into long-term planning for interstellar missions. Any attempt to send spacecraft to other star systems would need to account for the possibility of encountering hostile stellar responses that could destroy the mission before it reached its destination. Stealth technologies were investigated that might allow spacecraft to approach other star systems without triggering defensive responses. Electromagnetic shielding, reduced energy signatures, and passive navigation systems were developed to minimize the detectability of interstellar spacecraft. The technological challenges of interstellar travel in a galaxy with active stellar defenses were immense. Spacecraft would need to survive not only the harsh environment of interstellar space, but also potential directed attacks from target stars that might interpret their approach as a threat to system stability. As the fourth anniversary of the 3Y Atlas collision approached, the event continued to reshape humanity's understanding of cosmic dynamics and our place in the galaxy. The destruction of a single interstellar visitor had revealed that the universe operated according to principles that were far more complex and potentially hostile than anyone had previously imagined. The fragments of 3I Atlas, now dispersed throughout the solar system, served as permanent reminders of the day when humanity learned that even objects that survived million-year journeys between stars could be eliminated by stellar activity. Each piece carried information about interstellar processes and the active nature of galactic evolution. Long-term studies of fragment evolution provided insights into how interstellar material changed when exposed to stellar system environments over extended periods. The chemical and physical transformations observed in the fragments helped scientists understand the processes that shaped matter during its journey through cosmic space. New theoretical frameworks for understanding cosmic evolution incorporated the active role of stellar systems in shaping galactic structure and the distribution of matter throughout space. The traditional view of a passive universe governed solely by gravitational forces was replaced by dynamic models where stars actively influence their cosmic neighborhoods. The implications extended beyond astronomy to influence fields ranging from materials science to philosophy. Understanding how matter behaved under extreme conditions created by stellar activity opened new possibilities for technological development, while the discovery of active cosmic defense mechanisms raised fundamental questions about the nature and purpose of stellar evolution. Educational systems worldwide incorporated lessons about stellar dynamics and cosmic defense mechanisms into science curricula. Students learned that space was not empty and passive, but filled with active processes that could affect human activities and technological systems on Earth and beyond. The cultural impact of the 3I Atlas collision continued to resonate through human society as people grappled with the implications of living in a galaxy where stars could actively defend themselves against interstellar intrusion. The event had demonstrated that the cosmos was far more dynamic and potentially hostile than traditional scientific understanding had suggested. Religious and philosophical communities continued to debate the theological and existential implications of stellar defense mechanisms. Some interpreted the phenomena as evidence of divine design and cosmic purpose, while others saw them as demonstration of the universe's inherent violence and the isolation of intelligent life. The isolation theme became particularly prominent in philosophical discussions about humanity's cosmic significance. If stellar defense mechanisms prevented meaningful contact between civilizations, each intelligent species might be doomed to develop in isolation, forever separated from potential cosmic companions by natural barriers that no technology could overcome. Alternative interpretations suggested that stellar defense mechanisms might serve a beneficial purpose by protecting developing civilizations from premature contact with more advanced species. The natural quarantine provided by stellar activity might allow each civilization to develop its own unique characteristics without external interference. The protection hypothesis gained support from evolutionary biologists who argued that isolation might be necessary for the development of complex intelligence. Premature contact between civilizations at different developmental stages might disrupt natural evolutionary processes and prevent the emergence of truly diverse forms of consciousness. Economic implications of the stellar defense discoveries continued to manifest as industries adapted to new understanding of cosmic dynamics and space weather. Insurance companies developed new models for assessing risks associated with stellar activity, while technology companies invested in developing systems hardened against focused plasma events. The space industry underwent fundamental changes as companies recognized that future interstellar missions would face challenges far beyond the traditional hazards of radiation exposure and micrometeorite impacts. Spacecraft designs incorporated active defense systems and stealth technologies to minimize the risk of triggering hostile stellar responses. Commercial fusion power development accelerated as companies applied principles learned from studying solar focusing mechanisms. New reactor designs, incorporating stellar-inspired magnetic field configurations, promised to achieve controlled nuclear fusion with unprecedented efficiency and safety. Materials science industries developed new manufacturing processes based on the extreme conditions created during cosmic collisions. Products with properties that had never been achieved through conventional manufacturing became commercially available, revolutionizing everything from construction materials to electronic components. The medical industry benefited from research into how matter behaved under extreme conditions, leading to new treatments for cancer and other diseases that utilized controlled high-energy particle interactions. The understanding of plasma physics derived from stellar research opened new possibilities for non-invasive medical procedures. Agricultural systems incorporated enhanced monitoring for space weather effects that might influence crop yields and food production. The recognition that stellar activity could reach intensity levels affecting Earth's atmosphere and magnetic field led to development of more resilient farming techniques. Transportation systems worldwide implemented enhanced protection against electromagnetic effects from space weather. Airlines developed new routing systems that avoided areas of enhanced cosmic radiation during periods of increased stellar activity. Communication networks were hardened against focused electromagnetic pulses that might result from stellar ejection events. Satellite operators invested in shielding technologies and redundant systems to maintain connectivity during space weather emergencies. As the 5th anniversary of the collision approached, humanity had fundamentally altered its understanding of the cosmos and its place within galactic civilization. The 3I Atlas event had revealed that the universe operated according to principles that were far more complex, dynamic, and potentially hostile than traditional scientific models had suggested. The scientific legacy of the collision extended far beyond the immediate discoveries about stellar defense mechanisms and interstellar chemistry. The event had catalyzed developments in multiple fields of science and technology, leading to advances that benefited all aspects of human civilization. The fragments of 3I Atlas continue to provide scientific data about interstellar processes and cosmic chemistry. Long-term studies of how the fragments evolved under different environmental conditions throughout the solar system revealed new information about the behavior of matter during extended cosmic journeys. Space missions continue to intercept and analyze fragments as they disperse throughout the solar system and beyond. The extended duration of sample collection opportunities provided unprecedented insights into the complete range of materials and chemical compositions that had been present in the original interstellar visitor. The technological developments inspired by studying the collision had practical applications that extended far beyond space science. Advances in plasma physics, electromagnetic shielding, materials science, and energy generation all contributed to improving the quality of life for people around the world. International cooperation in space science and technology reached levels that demonstrated humanity's ability to work together when faced with cosmic-scale challenges. The global response to the 3I Atlas collision had established frameworks for international collaboration that continued to operate effectively years after the initial event. The event had also revealed the importance of maintaining continuous monitoring of stellar activity and space weather conditions. The Global Space Weather Consortium continued to coordinate observations from instruments worldwide, providing early warning of potentially hazardous stellar phenomena. Educational programs established in response to the collision continue to influence a new generation of scientists and engineers who understood the dynamic nature of cosmic environments and the active role that stellar systems played in shaping galactic structure. The philosophical and cultural implications of the collision continued to influence human thought and society. The recognition that stars could actively defend themselves against interstellar intrusion had fundamentally altered humanity's perception of its place in the cosmos and the possibilities for future expansion beyond Earth. As humanity looked toward the future, the lessons learned from the 3I Atlas collision provided both warnings and opportunities. The cosmos had revealed itself to be more actively structured and potentially hostile than previously understood. But the same phenomena that destroyed the interstellar visitor had also provided unprecedented scientific insights and technological advances. The active nature of stellar systems meant that any future attempts at interstellar travel would face challenges far beyond the traditional hazards of space exploration. However, the understanding of cosmic dynamics gained from studying the collision also provided potential solutions for overcoming these challenges through advanced technology and careful mission planning. The 3I Atlas collision had marked a turning point in human understanding of cosmic dynamics and galactic evolution. What began as the observation of a simple interstellar visitor had evolved into a comprehensive revelation about the active, dynamic, and potentially hostile nature of the universe itself. The fragments of the destroyed comet continued their eternal journey through space, carrying with them the chemical signatures of another star system and the story of humanity's first direct encounter with the active defense mechanisms that shaped galactic evolution. Each piece served as a permanent reminder of the day when humanity learned that even objects that survived million-year journeys between stars were not immune to the dynamic forces that governed cosmic civilization. The collision had demonstrated that individual cosmic encounters could have far-reaching consequences that affected entire planetary systems and influenced the course of scientific and technological development for generations. The universe had revealed itself to be a place where stars actively shaped their local environments and where the seemingly empty space between stellar systems was actually filled with dynamic processes that could eliminate interstellar travelers without warning. As humanity continued to study the implications of this cosmic revelation, the 3I Atlas collision remained a defining moment in human understanding of the cosmos, a moment when the universe revealed its true nature as an active, dynamic, and fundamentally interconnected system where stars themselves served as guardians of galactic stability and cosmic order.